Right, this section is going to be on galvanic cells. Now, normally when we've seen, redox reactions, um, like the overall net reaction between zinc and copper, electrons are transferred directly from the reducing agent, the thing being oxidized zinc, and the oxidizing agent, the thing being reduced copper. Now, what we're doing in this section is instead of just having this reaction, instead of just having this reaction occur in a solution, we're going to physically separate the agents so the transfer of electrons can take place via an external wire or an external conducting material. This is going to allow us to turn redox reactions and anodes and cathodes, oxidizing agents, reducing reagents, into electrical work. So an experimental apparatus for generating electricity is called a galvanic cell or voltaic cell. A galvanic cell, by definition, is harnessing the electrical potential of a spontaneous redox reaction. So if it's non-spontaneous, that's not a galvanic cell, otherwise known as a voltaic cell. What it does is it takes an anode, a place where oxidation is going to occur. You can see that the anode is a zinc solution, it was zinc sulfate, and a solid zinc anode. This solid zinc anode loses electrons, and zinc from that anode dissolves into solution, increasing temporarily the concentration of that zinc in solution. At the cathode, the opposite is happening. It's very similar to the anode's construction, the fact that you have a copper sulfate solution, so you have ionized the copper cation in solution, and you have a solid copper plate, but instead of copper dissolving and entering solution by being oxidized, it's the opposite. Copper is gaining, in solution, is gaining electrons and depositing on the cathode. So the copper bar is actually growing in size, whereas the zinc bar is dissolving in this. So that's the anode and the cathode. It's a spontaneous reaction, so electrons are passing through this wire, and when they flow from anode to cathode, there's a difference in electrical potential energy, and the difference is measured by this voltmeter, okay? Now, you would think that if you are at the anode and you have zinc that is dissolving and zinc cations are entering solution, and you have copper that is coming out of solution and depositing on the cathode, you're reducing the amount of positive charge in this solution. If you reduce the amount of positive charge in this solution and you increase the amount of positive charge in solution, that would cause these electrons to stop flowing after a while. The way that you resolve that conflict is you have a salt bridge. Now, this salt bridge consists of an inert salt in high concentrations that's just meant to balance out any charge buildup that might occur in the anode or the cathode. So the source of the charge changes in the anode and the cathode, but as zinc 2+ ions enter solution, the anions of potassium chloride come out to neutralize that charge, and as the copper 2+ ion concentration in the solution reduces at the cathode, the potassium from the salt bridge comes into play to balance out that charge. Now, once again, the voltage across the difference in electrical potential energy between the anode and the cathode is called cell voltage. Now, the voltage across the cell is measured by a voltmeter. Okay. Another common term for cell voltage is electromotive force, and albeit it sounds like it's a measure of force because force is in the name, it's actually a measure of voltage. And cell potential is the difference between the two. Now, this is a cell diagram for the galvanic cell that was on the previous slide. Now, a cell diagram is typically written as anode on the left. You can see that it goes from solid zinc, there's a barrier, phase boundary, and you have zinc in solution. This is representing the oxidation that happens at the anode. That's why there's dissolving at the anode. This double boundary right here is a salt bridge, right? That's what keeps the positive and negative potential constant across the electrodes. Even though the concentrations of these cations are changing, the salt bridge acts to make sure that, the positive and negative charge does not change. And on the other side, you can see the cathode, but the cathode's written a little different in the cell diagram, because instead of it going from the solid and you're dissolving zinc, releasing electrons to an external electrical source or conductor, it's the opposite. You have the solutions, and on the right side, you see it being reduced. So before we get into standard reduction potential, this is a general outline of what a galvanic cell is.